Okay, so in the last lecture, we started discussing about the semantics of Haskell, and we want to start with the denotational semantics. So the idea is we want to find a mapping from Haskell expressions to some values, to some mathematical objects. And we do this separately for every type. So we started with the base types, so the primitive predefined types like integers, booleans, characters, and floating point numbers. And well, the idea is that we map every expression of type int to a value from z bottom. So z are the integer numbers, and we extend the set of integers by an additional element bottom, which stands for undefined. So an expression, well, that evaluates to the number 5 will be mapped to 5, and an expression of type integer which whose evaluation doesn't terminate will be mapped to bottom. Okay, and the same will be done for booleans and characters and floating point numbers. So we take the natural values, but we extend them by an additional element, bottom for booleans, bottom for characters, and bottom for floating point numbers. And we can then compare elements by their definedness. And we had this relation here. So if we have such a domain of values, d, then we can say that some element, small d, is less defined or is identical to d prime, if and only if, well, for these base domains, either d is undefined or d and d prime are the same. So these base domains are flat domains. Well, either things are completely defined or completely undefined. So for example, z bottom looks like this. We have one undefined element, bottom, and we have many completely defined elements like 0, 1, -1, and so on. And these arcs indicate that bottom is less defined than 0, bottom is less defined than 1, and so on. But if we want to compare 0 and 1, well, we cannot do that, because 0 is not less defined than 1, and they are also not identical. And similarly, 1 is not less defined than 0, and they are also not identical. Okay, so these will be the domains for values of these primitive predefined types, like int and bool. And what happens if we have more complicated types, for example, product types? Well, there we discuss the product of domains. So if we have z bottom and z bottom, we can build the Cartesian product. And then the question is, how do we compare these tuples of values? And we do this component-wise. So if d is the domain consisting of domain 1 cross domain 2 cross domain 3 and so on up to domain n, then we can compare tuples like this. A tuple of values d1 to dn is less defined or equal to the tuple d1 prime to dn prime, if and only if this holds component-wise. So component number I in the first tuple is less defined or equal to component number I in the second tuple. And this must hold for all components, component 1, component 2, till component n. So for example, let's look at z bottom cross z bottom. And then we can see that we have, well, different stages of undefinedness. For example, this tuple, consisting of bottom, bottom, is less defined or equal to this tuple because we do this component-wise. And the first component, we have bottom, is less defined than 0. And in the second component, we have bottom here and bottom there, so they are identical. So by increasing the definedness of the first component, we get a little bit more defined. And from here, we can continue. So 0 bottom is less defined or equal than 0, 0, or 0, 1, or 0, 2. So we have different stages of undefinedness, but still only finitely many stages of undefinedness. But this changes when we move on to functions. So what will be the domain for functions? Well, a Haskell expression of function type should, of course, be interpreted as a function. So, for example, we now have domains like z bottom goes to z bottom. And again, we want to compare elements from these domains by their definedness. And we do this argument-wise. So if f and g are functions from d1 to d2, then we say that f is less defined or equal to g if this holds whenever we apply f and g to arguments. So for all arguments small d, we must have that f of d, so f applied to d, is less defined or equal to g applied to d. And, well, we will see later on that now we can have different stages of undefinedness, in fact, even infinitely many stages of undefinedness. Now, I said already in the last lecture that we do not need all of these functions when we speak about the semantics of programs, because there are some functions that are not even computable, and so they don't have to be included in these function domains. And to make this more precise, let's look at a concrete example and think about what is the semantics of some concrete Haskell function. Before we do this, we also introduced the notion of strictness in the last lecture. So strictness means that a function returns bottom whenever at least one of the arguments of the function is bottom. So we say that a function is strict if it has the following property. So f is a function of arity n. It takes n arguments and gives you back a result. And f is called strict if the following is true. Whenever one of the arguments is bottom, then the result is bottom as well. So the result here is bottom whenever one of these arguments is bottom. And of course, if two of these arguments are bottom, then the result is bottom as well. So it's sufficient to have one argument undefined, and then already the whole thing is undefined. If a function has this property, we call it strict. Okay, now let's look at a concrete example, and let's discuss what could be the semantics of such a function. And the function that we want to look at is the function 1. So this is a Haskell function, and it maps integers to integers, and it's defined like this. So 1 of x is 1. And the question is, what should be, to what function should we map this Haskell expression 1? So what should be the semantics of this? And well, there are different possibilities. Let me propose 3 possibilities, and then we discuss about the semantics of this. So what is the semantics of 1? So my first proposal is, let's say it's the following function. Well, it's pretty clear that as long as we apply the function to the number 1, to an actual number, the result should be the number 1. I mean, otherwise it doesn't really correspond to this definition. So f of x should be 1 for all x from z. But the question is, what happens if I apply the function to something undefined? So what happens if we apply f1 to bottom? And well, let's say if we apply it to bottom, the result is also 1. So that's one possibility. Another possibility would be to say, well, as long as we apply it to numbers, it's 1. But if we apply it to bottom, then the result should also be bottom. And maybe another possibility is to say, as long as we apply the function to numbers, the result is 1. But if we apply it to bottom, the result is something different, 0, for example. So these are 3 possible suggestions for the semantics of this 1. And what do you think? What should be the semantics of the Haskell function 1? Should it be f1, f2, or f3? Who's in favor of f1? Who's in favor of f2? And who's in favor of f3? Few people are in favor of f3. Okay, so that reflects more or less the reality. So the semantics of 1 in Haskell should indeed be f1. So this should be the semantics of 1. Well, what about the strictness of this function? This function is obviously not strict, because strict means that as soon as an argument is undefined, then the result is undefined as well. Well, here the argument is undefined, but the result is not undefined. So this is a non-strict function, but indeed these kinds of functions are useful in Haskell. And if you think of what Haskell does, I mean, if you apply 1 to something non-terminating, it will terminate and it will give you back 1. Because Haskell has lazy evaluation. Haskell evaluates from the outside. And so in Haskell we can really program these non-strict functions. So this is what we would expect from Haskell. So this is really a non-strict function. So this is what we would expect. But in fact, if we had a different programming language, so if this were not Haskell, but a different functional language like ML or Lisp, or if this were an imperative language like Java or C, then we would guess that this is the right semantics. So this is also a sensible function. This is a function which is strict, which returns undefined as soon as an argument is undefined. And if we had a programming language with innermost evaluation, then this would have been our choice. So this would be the semantics of one in a programming language with innermost or eager evaluation. With innermost evaluation. So this would be a strict function. And indeed, if we have a programming language with eager evaluation, then almost all functions that we program are strict. Now what about F3? Can we write, I mean, in Haskell, it's not so difficult to write a function that has this semantics. That should be possible. Yes? How would we do this? So how would a function with the semantics F2, how would we program this in Haskell? So let me call this 1 prime. So this should also go from int to int. But
X plus 1 subtract x.
X plus 1 subtract. Okay. Now I understand. So you want to say this is x plus 1 minus x. So something like this. Right. Because in order to evaluate, I don't know what binds stronger, so maybe like this. So in order to evaluate this, it will evaluate x. And if x is not terminating, then the whole thing will not terminate either. OK, true. Or no?
Just to say 1 prime and 0 equals 1. So it's the first one, and the second was the same.
OK. Or we say 1 prime of 0 equals 1, and 1 prime of anything else equals 1 as well. Yes, that would do it as well. Because if I apply 1 prime to something, it will evaluate this something to check whether it is 0. And if it's 0, fine. But if it's not terminating, then not so fine. So yes, both versions would do it. So indeed, it's not so difficult to write a function that has this semantics in Haskell. This one wouldn't do it, but both versions of 1 prime would do it. Now, can we also write a function that has the semantics F3 in Haskell? So it would be a function that looks at its argument. And if the argument is undefined, so if the argument is non-terminating, it returns 0. And if the argument is terminating, it returns 1. Yes?
Then we would have solved the halting problem.
Right. Then we would have solved the halting problem. And the halting problem, so F3 is the function that solves the halting problem. That would be very desirable, but this function is not computable. So this is the most famous example of a non-computable function. And therefore, we cannot program it in Haskell. And that's not the fault of Haskell, because in C or Python or Java or whatever, you can't program it either. So this is non-computable, because indeed it solves the halting problem. So the halting problem is the problem to decide whether some expression is terminating or not. And to solve the halting problem, you need a terminating function that investigates some other function or some other expression, and it finds out whether this thing is terminating or not, and it gives you 0 or 1 depending on whether it's terminating or not, and that cannot be done. So this is not computable, and therefore this is a function that we never need in our semantics, because, well, we cannot write programs that have this semantics. And so we could exclude these kinds of functions from our function domain, because they never occur. So let's do this. Let's exclude them. And, well, how can we distinguish, how can we characterize these functions that we want to exclude? So in general, a function f that well, it goes from one domain to another. These functions, I mean, they can look at their arguments and try to find out whether the argument is undefined. But as soon as the argument is undefined, well, they cannot return anything defined anymore. So the problem is that if the function is non-strict, so if I apply to bottom and this f returns something different from bottom. Now that's okay, that can happen because f1 does this as well. It returns something defined also for an undefined argument, but that may only happen if this argument wasn't really necessary for the result. So this is okay, but then it may not happen that for some other arguments, for some d, it returns something different than for bottom. For some d which is different from bottom. So if this happens, so f has to look at its argument, but it looks at its argument, and even if the argument is undefined, it returns something defined. That is not possible. So these functions are never computable. And so they should be excluded from the function domain. They should be excluded from function domains. And, well, we can characterize this in an even more general way. The function should have the following property. If we make the arguments more defined, then the result of the function should also become more defined. And if the function has this property, then we say it is monotonic. So let's define this property. And then we illustrate this by examples. So what is a monotonic function? Monotonic functions. So suppose we have two partial orders, one on D1 and one on D2. Let these be partial orders on D1 and on D2 respectively. On D1 and D2 respectively. Then we say that a function from D1 to D2 is monotonic if it has the following property. If I make the arguments more defined with respect to this order, then the result also gets more defined with respect to this order. So a function f from D1 to D2 is called monotonic if and only if D less defined or equal to D prime always implies that f of D is less defined or equal to f of D prime for all D and D prime from D1. So let's check the monotonicity of these functions f1, f2, and f3. So what about f1? Well, f1 is f1 monotonic. So suppose that D is less defined or equal to D prime. And here we have the domain Z bottom. Well, Z bottom is a flat domain. So if this holds, there are only two possibilities. So this means that either D is bottom, because bottom is less defined or equal to anything, or they are equal. So D and D prime are the same. Well, So what happens if I have f of d and f of d prime? So what happens with f of d and f of d prime? Does this hold? Well, if d is bottom, so here it holds because, well, f of d and f of d prime, well, as you can see, for f1, the result is always 1. It doesn't really matter what I apply it to. Even for bottom, the result is 1. So here we always have 1, and there we always have 1, so this clearly holds. So for f1, it holds. What about f2? Well, does it hold that f2 is less defined or equal to f2 d prime? Well, let's look at the first case. The first case is d is bottom. If d is bottom, then we have f of 2d, which is bottom. And f2 of bottom is bottom. And yes, clearly this is less defined or equal than f2 of d prime because bottom is smaller or equal to anything. And what about f3? Is this also monotonic? So here the answer is yes. And what about f3? Do we also have that f3 of d is always less defined or equal to f3 of d prime? No, why not? Well, let's say d is bottom and d prime is something else. I don't know. 1. So we have this. But f3 of bottom is not less defined or equal to f3 of 1. Why not? Well, f3 of bottom is 0, and f3 of 1 is 1. And 1 is not less defined or equal to 0. So the problem is that we make arguments more defined, but the result is not getting more defined or remaining equal. It suddenly changes. By making arguments more defined, the result changes from one completely defined value, namely 0, to another completely defined value. And that cannot happen if we have monotonic functions. And indeed, all computable functions are monotonic. So if your function violates monotonicity, then there is no program computing this function. So it's no problem to exclude the non-monotonic functions. So all computable functions are monotonic. Let's look at another example. For example, the identity function. Is the identity function monotonic? So suppose we have the following Haskell function which computes identity. So it of x is x. Then what should be the semantics of it? The semantics of it, well, it should be some function f, but the function f should be monotonic. So what should f do? F of x should be x for all integers. For all integers. And what should happen with bottom? If we want f to be monotonic, then there is only one single choice. So can it be 0? F of bottom, can it be 0? No, because bottom is less than or equal to 5, for example. But f of bottom, if it were 0, 0 is not less defined or equal to 5. So the only possibility is this must be bottom, otherwise it won't be monotonic. So this is the only possibility if f should be monotonic. And one possibility to guarantee monotonicity is strictness. So if you have strict functions which return bottom as soon as some argument is bottom, then you are on the safe side. Then it's always monotonic. But in Haskell, we have non-strict functions also in the semantics. So it's not enough to restrict ourselves to strict functions only. But the following lemma states, well, that strict functions are always monotonic. So this lemma says strictness implies monotonicity. Strictness implies monotonicity. So why is this the case? So suppose we have d1 to dn and another domain D. These should be some domains. And, well, the argument domains d1 to dn, they should be flat, where d1 to dn are flat. So things are either completely defined or completely undefined there. And now we have a strict function here. So let f be a function from d1 and dn to d, which is strict. Let this be strict. Then f is also monotonic. So how could one prove this? Okay, so what does monotonicity mean? It means that if I make the arguments more defined, then the result also gets more defined or remains equal. So this function works on tuples, so I have to make one tuple more defined than the other. So suppose that I have two tuples, and the first tuple from d1 to dn is less defined or equal than the second tuple from d1 prime to dn prime. And we have to show that then f applied to this is less defined or equal to f applied to this. So what do we have to show? We have to show that f of d1 to dn is less defined or equal to f of d1 prime to dn prime. Now, so there are two possibilities. Either these things are equal or it really gets more defined. So let's first look at the case where they are equal. If the first tuple is equal to the second one, well, then the claim is clear because, I mean, then these two arguments are the same. And so f applied to this is clearly equal to this. Then the claim follows by reflexivity. By reflexivity of this order here. And otherwise, if they are not equal, then, I mean, here, this relation on tuples is defined component-wise. So there must be some component which gets greater. So there must be some I with di is less defined and not equal, but strictly less defined than di prime. Now, how can that happen? Since this is a flat domain, the only way that something can really get more defined is if this is bottom and this is completely defined. So since di is flat, we know that small di is bottom. The bottom element of the domain di. And now, how does the rest follow? I mean, f is strict. We wanted to show that strictness implies monotonicity. If f is strict and one of these elements here is bottom, then f returns bottom as well. So as f is strict, we now know that f of d1, and here we have this di, dn, and this di is bottom. So if f is strict, then the whole thing here is bottom. Well, and bottom is less defined or equal to anything. So it's less defined or equal to f d1 prime up to dn prime. So as long as we have strict functions, we know they are always monotonic. But we have already seen with this function 1 up there that in Haskell we have lazy evaluation, and therefore we also need non-strict functions for the semantics. But since Haskell has lazy evaluation, therefore we also need non-strict functions. For the semantics. And well, here's another example where again we can illustrate why we need non-strict functions in the semantics. For example, the following conditional program which implements something like if then else. So cont takes a Boolean and two integers, and depending on the Boolean, it returns the second argument or the third argument. So cont of true and x and y. So if the first argument is true, it returns the second argument, and if the first argument is false, it returns the third argument. So this returns x, whereas if it's false, then we return y. So what should be the semantics of this? So the semantics of cont should be a function f which goes from which takes three arguments. The first one from b bottom, so the Booleans plus bottom. The second one from z bottom, and the third one also from z bottom. So b x y, and well, if b is true, then it should return x. So it should return x if b is true. And this also holds if y is bottom. So this is non-strict. As long as the first argument is true, it will only return the second argument. It will not care about the third one, even if the third one is undefined. And similarly, if b is false, it should return y. And now what happens if b is bottom? If this is the bottom element of b bottom, what should it return? X, y, or the number 15? Or something else? Well, if we want to make it monotonic, there's just a single choice. Because, well, think of bottom 5, 3. Now, if we would decide to return 5, this would not be monotonic, because if we replace bottom by false, we would suddenly return 3, and vice versa. So the only way to have this monotonic is to return bottom here. So otherwise, f is not monotonic. So there is no other possibility than that. And of course, this is a non-strict function because for example, we have f of true 5, bottom is 5. In other words, f is not strict, but monotonic. Okay, and we clearly need these kinds of functions. So we've now seen intuitively, if we have a Haskell function, what should be the semantics of it. But if you look at it, you will notice that the functions that we looked at up to now are pretty easy. They are not recursive. So they had no recursive calls, and as long as they have no recursive calls, well, finding the semantics is pretty straightforward. But what happens if we have a function with recursive calls? And of course, in reality, all interesting functions are recursive. So how can we then determine the semantics of such a function? And to explain that, we need a new concept, another mathematical notion, the notion of a chain. But first I have to wipe the board. Okay, so let's again look at what we did up to now for these different domains. We've seen that there are different stages of undefinedness. For tuples, we had this tuple with 2 bottoms, and then just with 1 bottom, and then with no bottom anymore, and this got more and more defined. And these sequences of elements that get more and more defined, such sequences are called chains. So chains are, in some sense, sets of elements that get more and more defined. That get more and more defined. So for example, something like bottom, bottom, and then we replace one of these bottoms by a concrete number, and then we replace the other bottom by a concrete number as well, and you can see that we get more and more defined. And in general, these chains may be infinitely long, and we will see an example of this in a minute. So the definition of a chain is as follows. We have some partial order on some set, so this should be a partial order on some set D. Then we say that a non-empty set D1 to D2 and so on. And this set can be finite or infinite of countably many, abzählbar viele in German, of countably many elements from D is called a chain, Kette in German, if and only if they can be ordered. So they can be ordered like this. Some element is less than or equal than the next element, and this is less than or equal than the next element, and so on. So that's the definition of a chain, and these chains can be finite or infinite. So, for example, the set containing these 3 tuples up there, so bottom, bottom, 5 bottom, and 5 8. This set with these 3 elements is a chain. Of course, a finite one because it contains only 3 elements. This is a chain, and of course we would like to see whether chains can also be infinite. Well, with tuples, there is no way to get infinite chains if we just have tuples of integers. But if we have functions, then we can indeed have infinite chains as well. So let's look at an example for an infinite chain. How can we get this? Well, let's look at a family of functions. So we have lots of functions, and they are all approximating the factorial function. So therefore I call them fact, but they have an index I. And they all go from z bottom to z bottom. And they do almost the same as the factorial function, but not quite. But one function after another, I get closer to the real factorial function. So in some sense, they are approximations to the factorial function. So fact 0, that's a very poor approximation to the factorial function because it always returns bottom for all arguments, for all x elements z bottom. Now that's not a very good approximation to the factorial function, but the next one gets already a bit better. So fact 1 is a bit better. It returns the factorial of x, but not for all x. In fact, it only returns this for, well, non-negative numbers that are smaller than 1. Now, this is an unreadable version to write x equals 0. So it returns the factorial for 0. The factorial of 0 is 1. And, well, for negative numbers, I don't know how the factorial is defined for negative numbers, so I defined it to be 1. So for negative numbers, it returns 1, and otherwise it's undefined. So if x is bottom or x is greater or equal than 1, then it's undefined. Well, if we say that the factorial for negative numbers is indeed 1, then this does the right thing for all numbers less than or equal to 1. So in particular, this is defined for all x less or equal to 0. So this does the right thing for negative numbers and for 0. For larger numbers, it's not doing the right thing, but the next approximation is better. So fact 2, it does the right thing. So it computes x factorial for all positive numbers that are smaller than 2. So in other words, for 0 and 1. And for the rest, it behaves like fact 1. So it gives you 1 for negative numbers, and it gives you undefined if x is undefined, if x is bottom, or if x is greater or equal than 2. So the numbers where this is defined have increased a little bit. So this is defined for numbers that are smaller or equal to 1. Okay, and you can imagine how this continues. So fact n then does the right thing. So it computes the factorial for positive numbers that are smaller than n. For negative numbers, it computes 1. And otherwise, it computes bottom. So if x is bottom or x is greater or equal to n. So this is defined for all x less or equal to n. So as you can see, with each iteration, I increase the set of numbers where the function is defined by one more element, and slowly but slowly I converge against the real factorial function, because the real factorial function is defined for all positive numbers. And here it takes a while, but if I wait long enough, then I get closer and closer. And, well, is this a chain? I would say yes, because if you remember how to compare functions for definedness, here you can see it again. If we want to compare functions for definedness, we do this argument-wise. And so fact 0 for sure is less defined or equal to fact 1. Because, well, this is not defined anywhere. This always returns bottom. And this is at least defined somewhere. It returns bottom for many numbers, but not for 0 and not for negative numbers. For 0, it returns 1, and for negative numbers, it also returns 1. So this is, for each argument, it's either bottom or it's 1. So this is clearly more defined or equal to fact 0. Now fact 2, in fact, fact 2 is almost the same as fact 1. There's only a single argument where they differ, namely the argument 1. Fact 2 of 1 is the factorial of 1, which is 1. And fact 1 of 1 is bottom. So here we have bottom, here we have 1, so this is increasing. And for all other arguments, it remains the same. And fact 3 is almost the same as fact 2, except for the argument 2. Here it gives you the factorial of 2, which is 2. And here it gives you bottom, and so on. So you can see that this is an infinite chain of functions. The set of arguments where this is defined increases in each iteration, and, well, it increases forever, so this is infinite. And we will need these kinds of functions to define the semantics of recursively defined functions. Because if you want to program factorial in Haskell, you would do this by a recursive definition. And, well, when you want to describe what is the semantics of this definition, we will need these kinds of functions. Why? Well, fact 0 represents something like, well, OK, fact 0 is always undefined. Fact 1. Fact 1 more or less states that as long as you don't need a single recursive call, fact 1 does the right thing. But if you need a recursive call, this suddenly says undefined. Fact 2 does the right thing as long as you need only one recursive call. Fact 3 does the right thing as long as you need only two recursive calls, and so on. So for each iteration, one of these, for each argument, one of these functions does the right thing. But depending on how large your argument is, you might need facts with a high index. We will see this later on. So we have these kinds of chains, and these chains can be infinite. And they approximate the real thing. We have seen that these functions, they get more and more defined, and so they converge towards the real factorial function. And this form of convergence, we want to express this formally. Well, and what this converges to is, in fact, just the least upper bound of all these functions. I mean, we can compare these functions by definedness. So we can also speak about upper bounds of these sets and also about the smallest, the least upper bounds. And let's define this formally, and then we see what the least upper bound of this chain is. So for chains, it is often interesting to find their least upper bounds. To find their least upper bounds. So what is a least upper bound? Let's define it. Definition 2.1.10. What is the least upper bound of some set? So we have some partial order. Let this be a partial order on a set T. And we have some subset S of D. So first, what does upper bound means? And then I explain what least upper bound means. So an element small d from capital D is an upper bound of S. Is an upper bound of S. Well, upper bound means that this D is greater or equal to every element in this set S. So for all elements D prime in S, we have that D prime is less than or equal to D. If this holds for all D prime from S. So this is the meaning of upper bound. And what does least upper bound mean? Well, it's an upper bound, but it's small or equal to every other upper bound. So an upper bound D is the least upper bound. We also call this the LUP. So this is just the abbreviation of least upper bound, or you can also say the supremum. So it's the least upper bound of S if, well, it must be an upper bound, and moreover, for all other upper bounds E of S, we have that, well, D is less than or equal to E. And the notation is the least upper bound of S is also often denoted as, well, this is the less than or equal relation turned around by 90 degrees. And this notation means least upper bound of S. So let's look at some examples. So if we look at the following chain, how many upper bounds does this set have? This chain, does it have upper bounds? And if so, what are the upper bounds? Upper bounds with respect to the less defined or equal relation. Mm-hmm.
It's a tuple of 5 and 8.
Right. So this has only one single upper bound, namely the tuple of 5 and 8. And since this is the only upper bound, it's also the least upper bound. It is also the least upper bound of this chain. Now, what about this chain with fact 0, fact 1, and so on? So fact 0, fact 1, and so on. Does this also have upper bounds? Well, I would say yes, and in fact it has many upper bounds, infinitely many upper bounds, in fact. So this has infinitely many upper bounds. So how would these upper bounds look like? Well, I mean, these are functions. So the upper bound is also a function which goes from z bottom to z bottom. So infinitely many upper bounds f. And, well, these f's must be functions. And how are these functions defined? To make them upper bounds, they must be greater or equal to fact 0, to fact 1, to fact 2, to each of them. And, well, and functions are compared argument-wise. So let's first look at negative numbers. So if x is negative, then fact 0 gives you bottom, fact 1 gives you 1, fact 2 gives you 1, fact 3 gives you 1, and so on. And so to be an upper bound, this should be greater or equal to bottom, and to 1, and to 1, and to 1, and to 1. So there's not much choice. It must be 1. So for negative numbers, this function must return 1. Now, what about the positive numbers? What about 0? So if x is 0, fact 0 of 0 is bottom. Fact 1 of 0 is the factorial of 0. Fact 2 of 0 is the factorial of 0, factorial of 0, factorial of 0, and so on, and so on. So we have to be, for 0, we have to return something which is greater or equal to bottom and to the factorial of 0. Yeah? So fact of 0 is bottom, but fact 1 of 0 is 0 factorial. Now what happens if we apply this with 1? So factorial 0 of 1 is bottom, fact 1 of 1 is also bottom, but fact 2 of 1 is the factorial of 1. And so since f has to be an upper bound, for the argument 1, we cannot return bottom, but we have to return the factorial of 1. And well, for 2 it looks similar. So here we have bottom, but if we go long enough, then factorial of number 3 of 2 is the factorial of 2, and so on. And in fact, so for every positive number, we have to return its factorial, because this has to be an upper bound of all these functions in here. And if we go further over here, then at some point we will reach one of the functions where the result is not bottom, but it's the factorial of the argument. So we have to return the factorial of x for all x's that are greater or equal to 0. Okay, and so the only thing that remains is, what do we do if x is bottom? Well, if x is bottom, all of these functions return bottom. And if we want an upper bound, we can return anything, because anything is greater or equal to bottom. So here, the result is completely arbitrary. And this is the reason why we have infinitely many upper bounds. So for example, the function that computes the factorial for positive numbers gives 1 for negative numbers, and 42 for the argument bottom would be an upper bound. But of course, if we restrict ourselves to monotonic functions and to computable functions, then there are not too many choices anymore. Then we are pretty much limited, and we know what to return. Then we have to return bottom here. Otherwise, this will not be monotonic. So there are many upper bounds, but only one that is monotonic. So only the function with f of bottom is bottom. This is the only of these functions that is monotonic. Is monotonic. And this is also clearly the smallest of all of these f's. So this is the least upper bound. This is also the least upper bound of this chain of fact 0, fact 1, and so on. So we might now ask ourselves, do these least upper bounds always exist? So whenever we have a chain, is there really a least upper bound? And if there is, how can we compute it? How can we get it? And there, the following lemma can be useful. So when do least upper bounds exist? And how can one compute them? And this is partly answered by the following lemma. And this lemma says that how do we get least upper bounds for chains of functions and for chains of tuples? So least upper bounds for products or tuples and functions. So we have some domains, d1 to dn, and also d and d prime. And well, part A says something about tuples, and part B says something about functions. So we have, if we speak about tuples, we have some subset of d1 cross dn. And the question is, how can we get the least upper bound of such a set of tuples? And the lemma says, well, look at the projections for each component. Build the least upper bounds for all these projections and then put it together. That's the least upper bound for this whole set. So let's build the projections by only looking at the first argument and only looking at the second argument and so on. So if we do this for all I between 1 and n, let's build the projection that looks only at the ith component. So Si are all values that occur in component number I. So these are all di which at some point occur at the ith position in such a tuple. So whenever there exists some tuple d1, and here we have di, and here we have dn in S. So we do all these projections, and then the lemma states the following. There is a least upper bound for the whole set S if and only if there are least upper bounds for all these projection sets. If all least upper bounds for S1 to Sn exist. And moreover, it also tells us how to get this least upper bound of S. So if this least upper bound of S exists, then it looks like this. It's the tuple where the first component is the least upper bound of S1, the second is the least upper bound of S2, and the last is the least upper bound of Sn. So this means if we want to compute the least upper bound of such a set of tuples, we can build these projections, we compute their least upper bounds, and then we put them together into one tuple again, and then that's it. So let's do an example before I continue the lemma. So before I continue the lemma, let me illustrate this by an example. Suppose that S is the set of pairs that we had before, bottom, bottom, 5, bottom, and 5, 8. Then what is S1? Well, S1 is the projection on the first argument. So here the first argument is bottom. Here the first argument is 5. Here the first argument is 5 as well, but we had 5 already in the set. So these are all the components that occur in first components somewhere. And what is S2? It's the projection on the second component, so it contains all elements that occur in the second component somewhere. So bottom. Here's also bottom, but we had that already. And there it's 8. And what the lemma says is that if I want to compute the least upper bound of S, I can first compute the least upper bound of S1 and S2. So what's the least upper bound of S1? Well, the least upper bound of this set, something which is greater or equal to bottom and to 5. Well, that's 5, obviously. And the least upper bound of S2 is obviously 8. And the lemma says if I want the least upper bound of S, then I can take the tuple containing the least upper bound of S1 and of S2, and that's it. So it's 5, 8. Okay, yes?
If we required S to be same, could we prove that there is always a least upper bound?
No. That is a special property that we have to add, and indeed we will require this afterwards. So we will say that an order is called complete if every chain has a least upper bound. So that's a special property that we have to require. So in general, that's not certain. For example, if you think of all think of all non-total functions. So let's say this is a set. And in this set, so fact 0, fact 1, fact 2, and so on, they are all not total because there are some numbers where they return bottom. But in this set of non-total functions, this chain has no least upper bound because the only least upper bound is total. That's the factorial function that is defined on every number.
Okay, so the least upper bound exists.
It exists, yes, but it is not part of, it exists somewhere, but it's maybe not in your domain. And therefore
So we could
Well, no. No. So really, this is something you have to require extra, and we will require this, and then we can rely on the fact that they always exist. But this you cannot take for granted. But let me continue with this lemma, because up to now we had only part A, and of course there's also part B. And part B says more or less the same thing, but about functions. So now S is not a set of tuples, but a set of functions. So let S be a set of functions from D to D prime, from D to D prime. And now again, instead of tuples, we now have functions. And for functions, if we want to have the least upper bound, we can do this argument-wise. So for all I from D, let Si be the projection on this argument. So it contains the values f of I for all f from S. So we take all the functions in the set and apply them to this argument I. And we do this for every argument. And now what the lemma says is we could build the least upper bounds for all these SIs. And if they all exist, then we create the least upper bound for S by putting all of them together. So it says more or less the same as for A. The least upper bound of S exists if and only if the least upper bound of Si exists for all I from D. And moreover, if the least upper bound of S exists, then we know how to get it. Well, this must be a function. So it must also be a function from D to D prime. And what does it do? If I apply it to some I of D, then I get the least upper bound of Si. So this is essentially the same as part A, but this time for functions. Let's prove it. I will only prove part A. The proof for part B is completely analogous. So this is the proof of A. Okay, so what do we have to show? Let's first show the direction from right to left. So what we want to show is the following. If all of these least upper bounds for these projected sets exist, then the least upper bound of S exists as well, and it's the tuple consisting of all of these components. So then the least upper bound of S1 to the least upper bound of Sn is the least upper bound of S. This is what we want to show. Okay, to show this, we want to show that this is an upper bound and in fact even the least upper bound. Let's first show that it's an upper bound. So we take some element from here and show that this thing is greater or equal than the element from S. So let D1 to Dn be from S. And so this implies that D1 is from S1, D2 is from S2, and so on. So for all I, we have that Di is from this projection set, which only looks at the ith component. And therefore, each Di must be smaller or equal than the least upper bound of Si. So Di is always smaller or equal than the least upper bound of Si for all I. And this means that the whole tuple D1 to Dn must be less than or equal than this tuple of the least upper bounds of S1 to Sn. So in other words, so this is really an upper bound of S. So this is an upper bound of S. Is an upper bound of S, and it remains to show that this is the least upper bound. Now we show that this thing is smaller than every other upper bound of S. So let's take another upper bound of S. So let E1 to En be another upper bound of S. And then in particular, this means that if I look at the ith component here, then this ith component here is greater or equal to all the ith components occurring in S. So this means that EI is an upper bound of all the ith components in S for all I. But if EI is an upper bound of SI, then the least upper bound of SI must be smaller or equal than EI. So since this is the least upper bound, it must be smaller or equal to EI. And since this holds for all components, we have that the least upper bound, the tuple of all these least upper bounds is less than or equal to E1 to En. And so now we have shown that this thing is an upper bound, and it's less than or equal to every other upper bound, and therefore it's the least upper bound. So this was the direction from right to left. And now we still have to show the direction from left to right. So from left to right, now we assume that the least upper bound of S exists. So it has the form, well, it's some tuple U1 to UN. And what do we have to show? We want to show that the ith component in here is the least upper bound of SI. Is least upper bound of SI for all I. Okay, so it should be the least upper bound. So let's first show that it is an upper bound at all. First show that UI is an upper bound of SI. So to show this, let's take some element from SI, some DI. But if this is a component in SI, then there must be some tuple in S where this DI occurs at the component number I. And since U1 to UN is an upper bound of S, we know that this component here is less than or equal to this least upper bound of S. So if this is an upper bound of S, then it must also be greater or equal than this. But then the ith component must also be greater or equal than this. So since we have this, we also have that DI must be bounded by UI. So yes, this UI is an upper bound of SI. And now we have to show that it's the least upper bound. Now show that ui is the least upper bound of Si. And well, again, the same trick as before. Let's assume there's another upper bound of Si. So let ei be another upper bound of Si. And then this implies that I can, from this, construct another upper bound of the whole set S. Namely, I take all these u's, but I replace ui by ei. So is another upper bound of S. But if this is an upper bound, then the least upper bound must be smaller. So since this is the least upper bound of S, we have that this thing is less than or equal than this thing. So u1, ui, un, this one must be less than or equal than the new one where we replaced ui by ei. And since this is defined component-wise, we obtain that ui is less than or equal to ei. And so this must really be the least upper bound of Si. It must be smaller or equal to any other upper bound of Si. So this is just playing around with the definition of least upper bounds. Yeah, okay, this was only the proof for part A, but the proof of part B is analogous to the one of part A. So this is not a very deep theorem, but yeah. And to finish up, let's formally answer the question that you just asked. Does every chain always have a least upper bound? And the answer is no. This is something that we should require in addition. And that leads us to the last definition for today, namely the definition of completeness. So this is the definition of a complete partial order, or CPO for short. And this says that a reflexive partial order on a set D is called complete if it has two properties. One property is harmless, namely that's the property that there must be a smallest element. So D has a smallest element which we typically denote by bottom D. And the second property is that every chain indeed has a least upper bound. Every chain S in D has a least upper bound, which is also element of D. And indeed, the domains that we regarded up to now, they are all complete. So they have a smallest element, and they have this property. And, well, we will look at this again in the next lecture and see why they had this property. And we will make sure that all the domains that we regard in the future have this property as well. So the next lecture is on Friday, and on Wednesday there's the exercise course. And a new exercise sheet is also on the web today, I hope. OK, see you on Friday.